All right. I'm rather happy about this review page that I made for you. I think if you could just fill it out twice, you would really know everything that you needed to know about graphing the trigonometric functions. This is all in your notes, except for the only thing I added to this equation is I threw a vertical shift on there so that I could ask you what's the vertical shift. But I want to make sure that you understand, because I think for some of you it's clicked and some of you it hasn't clicked yet. When you're looking for values or when you're graphing sine, the x coordinate is number of radians. And for sine at x radians, you just take the y coordinate. For cosine at x radians, you just take the x coordinate. For tangent, you just divide the y coordinate by the x coordinate. So if you're looking at the ordered pairs here, I'm going to go ahead. I had this attached to an email last night. If you checked your email, you saw it. I also uploaded it to Momentum in case you didn't check your email. So if you don't have that now, it's absolutely fine. Just print it and use it this weekend because I think it'll be helpful. It'll be helpful review to you, just like the blanks unit circle allowed you to go around the unit circle labeling everything you needed to label. So real quickly, I know we reviewed this yesterday and that's how we got so far behind, the whole day behind, but this is worthwhile if it hasn't clicked for you yet. So I'm just going to do one of these and I'm going to leave the other 5 for you to do and then print blank copies, do it at least twice this weekend. All right, here's what I'm thinking. At pi over 2, or no, at 0 radians, sine is the y coordinate 0. At pi over 2 radians, sine is the y coordinate, which is 1. At pi radians, sine is the y coordinate 0. At 3/2 pi, sine is the y coordinate, which is -1. And at 2 pi, sine is the y coordinate, which is back to 0. So this is the shape that you should have in your head for sine. And if we graphed sine and cosine from -80 pi to +80 pi, they would both just look like a bunch of squiggles. But I'm talking about over one interval, 0 to 2 pi, over that interval, sine and cosine look different. If you just chose this little part of sine, it would look like cosine. But if we look at them just 0 to 2 pi, they are different. The amplitude of sine is 1, the period is 2 pi. The endpoints of the period that I used are 0, 0, and 2 pi, 0. The midpoint of one period, the period that I chose is 0 to pi. Here's what's just a little bit different when you have a graph that has been maybe had a change in amplitude, a change in period, shifted somehow. I want you to know that technically, absolute value of A gives you the amplitude. How do you find the period for any trigonometric function that has shifts in it? Normal period, whatever it is, divided by the coefficient of B. This is normal period, 2 pi, divided by the coefficient of X, which is B. The vertical shift for this graph is down D units, and define the endpoints of one period. You set that argument between 0 and 2 pi. So that's all you need to know about the graph of sine. And you saw how quickly I filled it out by just thinking about the y coordinate as I go around the unit circle. I want you to do the same thing for the other 6 after we talk about secant today. Secant's the only one we haven't talked about. That's in Momentum and it's in your email. So let's finish this up. Let's talk about secant. Secant, we know, is the reciprocal of cosine. As we go around the unit circle, how do you determine the cosine at each of our common angles? Cosine is your x, so secant will be 1 over your x. And as we go around the unit circle, 1 over x is going to be undefined wherever cosine is 0. Is cosine 0 your half pies or your whole pies? Yep, cosine is 0, x is 0 at your half pies. So I already know that at half pi, all the odd half pi radians, secant is going to be undefined. And what do we know that tells us about the graph where the function's undefined? That's where the vertical asymptotes are. So vertical asymptotes at all the odd half pies. And the domain is anything except for those odd half pies. So x cannot be, you remember how we wrote odd half pi? How did I write odd? Definition of odd is double a number and add 1. So if n is any integer, then 2n plus 1 is an odd number, right? 2n plus 1 is an odd number, and so that's odd half pies, all of your odd half pies. We'll wait just a minute before we decide which of these asymptotes to use for one period. Let's think like we did for cosecant. What interval, what quadrants, that's what I want, what quadrants would be from negative pi over 2 to positive pi over 2? That's the first and fourth quadrant. What do you know about the sign of secant in the first and fourth quadrants? Yeah, your x's are positive in the first and fourth quadrant. So this portion of the graph, which I wish I hadn't put that bracket right there, the function has to be positive. It can't do an x cubed thing or a negative x cubed thing, can't do a positive x cubed thing, can't do a concave down thing. It has to be concave up over that interval. And actually, before I talked about that, I meant to go back and fill in these other values on my XY chart. At negative 2 pi, what is secant? Negative 2 pi is the same as positive 2 pi. The x coordinate or cosine is 1. The reciprocal of 1 is 1. At negative pi, that's the same as positive pi. Secant would be negative 1. At 0, secant would be 1 again. At pi, secant would be negative 1 again. And at 2 pi, secant is 1 again. So if I plot those points, negative 2 pi 1, negative pi negative 1, 0, 1, pi negative 1, 2 pi positive 1, I can tell what we got based on what I remember about cosecant and what we figured out here about quadrant 1 and 4. I can pretty much guess what the rest of that graph is going to look like. It's going to have a concave up UE, a concave down UE, just like cosecant did, but in a different place. So here's the concave down, Here's a concave down. That's part of a concave up. That's part of a concave up. How large of an interval do you think we'll have to get one complete picture of everything secant's ever going to do? Just like cosecant, it takes a whole interval of 2 pi to get both a concave up UE and a concave down UE. So for one interval, for one period, I mean, we could use from -3/2 pi to +1/2 pi. That would contain both the concave down and the concave up. Or we could use 1/2 pi to 3/2 pi. And I'll tell you why I prefer to use 1/2 pi to 3/2 pi. If that's the interval I choose, then I can remember just like cosecant, there's a concave up before a concave down if I use that interval for one period. So where's my highlighter? I'm going to use from -pi/2 to 3/2 pi. And that will give me a concave up before the concave down. Now, Hallie, does that answer the question you asked me before class? Okay. So for our left and right vertical asymptotes, we're going to use x = -pi/2 to 3/2 pi. Which makes our middle asymptote what? Yeah. Halfway between these is pi/2. Make sure you're writing that as an equation, not just some number. What's the range of secant? Xavier, can you help me with that?
-. Would it be -infinity to -1?
Yep.
And connected, and then 1 to
Perfect. It would be -infinity to infinity, but there's y values in between the concave up and the concave down that secant's never going to hit. So we have to say it is from -infinity up to 1, -1, including the -1, and then also from 1 to infinity. And what did y'all tell me the period of secant is? Miss Elizabeth? It takes a whole 2 pi units for secant to do its whole thing. And we're only choosing this period from -pi/2 to 3/2 pi to get one complete concave up before one complete concave down. Brady, what's your question? Let me, 2n + 1 is just the way we say odd. All right, so what are the only two functions that don't have a period of 2 pi? And cotangent. And they have periods of what? 1 whole pi. Yeah, tangent and cotangent have a period of 1 whole pi. All right. So if a graph has been shifted and compressed or expanded or something going on, you can still get its period by dividing the normal period for secant by the coefficient of x. And to find the left and right asymptotes for one period, you understand why we set that bx plus c between -pi/2 and 3/2 pi? That's just the period of 2 pi that we chose. We could have chosen any 2 pi, but we chose this to get 1 complete up before 1 complete down. All right, let's do it. Secant of x minus 3 pi over 4, we start with kind of the easy one that only has a horizontal shift on it. The general shape of one period of secant, we know 1 concave up, 1 concave down, but I think it would be helpful to you if you went ahead in that rough sketch and told me where those asymptotes were. I think it'll help you when they get shifted. So that left and right asymptote are negative pi over 2 to 3/2 pi. And the middle one is pi. When you just ask me what secant looks like, that's the mental image that pulls up real quickly. All right, how do I find the period of this function? Two pi, because that's the normal period for secant, divided by the coefficient of x, which in this case is just 1. So this function also has a period of 2 pi. Pi over 2. Pi over 2. Thank you very much. Yep, that's not the mental image that should pop up in my head. It should be pi over 2. Don't know what I'd do without you, Miss Elizabeth. All right, so how do I find the left and right asymptotes of this function? Because that's your normal left and right asymptotes if the graph hasn't been shifted. So I'm going to set that x minus 3/4 pi between negative pi over 2 and 3/2 pi. And then I'm going to add 3/4 to all 3/4 pi to all 3 sides of that equation. Again, in my happy bubble, y'all are practicing not having to touch your calculator to add fractions. Because if you practice, you can add fractions faster than the calculator can. But if you're not sure, double check yourself. I don't want you to miss this problem on the test because you added 3/4 and negative 1/2 incorrectly. All right, this add 3/4 pi to both sides and you'd have 3/4 minus, this is 2/4 is 1/4 pi. And this is 3/4 plus 6/4 is 9/4 pi. And then what's my nice built-in check right here? Actually, you subtract to see if you get 2 pi. You're looking for the length of this interval, and to find the length of the interval, you subtract. So 9/4 minus 1/4 is 8/4. Sure enough, that's 2, like I knew it should be. If my left and right asymptotes are pi over 4 and 9/4 pi, what does that mean my middle asymptote is? You just add them, that's 10/4, and divide by 2, that's 5/4. So x equals 5/4 pi. On the C part, I didn't actually write down my 2 equations. I should have done that. X equals pi over 4 and x equals 9/4 pi. So let's count by quarter pies. Label at least one. Quarter pi, 1/4, 2/4, 3/4, 4/4, 5/4. 6/4, 7/4, 8/4, 9/4. There's your left asymptote, your right asymptote, your middle asymptote. Which one of those was 5/4? 1, 2, 3, 4, 5. That one was 5/4. Halfway between pi over 4 and 5/4 pi, what should this graph be doing? What should it look like? And these normally turn around at 1. If this secant had a coefficient other than 1, that's where the graph would turn around. If this was 2 secant, then the graph would turn around at -2 and +2 instead of -1 and +1. But since that coefficient is 1, and since we're using the same period that we used for this, you get your concave up UE before your concave down UE. Does anybody need to ask me anything? Give me somewhere between thumbs down and thumbs up. This is so-so. How much sense is this making now? How much better do you feel about graphing now than you did, say, Monday? Okay. And if you're not totally thumbs up, you're gonna work with me, and if we have to jump on Zoom this weekend, we will. Okay. All right, let's do one more secant. And then I wrote down the one example of cosecant we didn't do yesterday, but because we're a day behind, I think if we do number 2 and feel okay with it, we might just go on and get a little bit of a head start, well, catch up, not head start, on 4.7. I brought that with me too. All right, so general shape of one period of secant. You do that. Give me just what should be in your head when you think of one period of secant. All right. How do you get the period of this function? Silas, would you help me with that?
You take 2 pi by 2.
Okay, 2 pi, the normal period, divided by the coefficient of x is just pi. Good job. This graph is going to do its whole concave up and concave down in just a period of 1 pi. Colby, remind me how to find one pair of asymptotes. Because that's what we chose for our left and right asymptotes of just the basic function. Good job, Colby. I'm going to set that between -pi/2 and 3/2 pi. And then I'm going to add pi/6 to all 3 sides. This is -3/6 plus 1/6 is -2/6, better known as -pi/3. Or punch it on your calculator. This is 9/6 plus 1/6 is 10/6, better known as 5/3 pi. and then divide all three sides by 2. Negative pi over 6 is less than x is less than 5/6 pi. And here's the big check to make sure I solved correctly. Is that really a distance of 1 pi unit? Yep. 5/6 minus negative 1/6 is 1. 1 pi unit is the period. All right. If my left and right asymptotes are x equals negative pi over 6 and positive 5/6 pi, what's my middle asymptote? All right, and if I add those together, I get 4/6, better known as 2/3 pi. Divide it by 2, I get 1/3 pi. X equals pi over 3. So what do you think I'll count by on my x-axis? Yeah, your pi over 6 is your smaller increments. That's just 2/6 pi when we get to it. All right, so negative pi over 6, 1/6, 2/6 is pi over 3, 3/6, 4/6, 5/6 pi. Don't tell me what else. What have I done?
On the x, you've got negative pi over 6 and 5 pi over 6. You add those together, you get 4 over 6, not 2 over 6, which is what you did in the middle asymptote.
I thought I said, I wonder if this is a case of said the right thing, wrote the wrong thing. I think I said the right thing. And sometimes.
I had to change the fraction.
Well, every time, every time I get sassy about y'all not being careful and not making mistakes, I make a mistake. That's what keeps me humble. All right, let me see. 5/6. I'm adding divided by 2. 5/6 and negative 1/6 is negative 4/6, which,
Just 4/6.
yeah, 4/6. 4/6 divided by 2 is 2/6. Better.
No, it's 2 pi over.
I need to write it down.
Writing
Negative,
things down helps.
it does. When I'm going fast, I try to do everything in my head. Negative pi over 6 plus 5/6 is 4/6, better known as 2/3 pi. I'm still coming up with pi over, 2/3 pi. Yeah, not, yeah. Huh.
No, because to get the middle, you just add them.
Uh-huh.
And go for the very middle, which is 2 pi over 3. There's
You add them and then divide.
I
by two.
added them and got 2/3, but then when I take a half, I get 1/3.
4 over 6 divided by 2 is 4 over 12, and then that's 1/3.
okay, yeah.
Whew. All right. Yeah, half of that would be pi over 3. Let me show you one other trick. I don't remember if I've mentioned this before. I've thought of it several times and maybe just didn't stop to say it. If you're counting by some consistent value on your tick marks, which you should be, you can make sure that there's the same number of tick marks between the left and the right asymptote as there are between the middle, same number of tick marks between the left and the middle as there are between the middle and the end. Make sure you're counting 0 as a tick mark. And then between these two, there's 2 tick marks. Between these two, there's 2 tick marks. That also helps me as another built-in check, and y'all know how OCD I am about checking. So far so good? That's a funny look, Dominic. As good as I've ever been. Can you ask me anything that would help? Okay. Left asymptote right asymptote, middle asymptote. And the only thing that we haven't accounted for yet is this half. And maybe y'all can help me think of a good way to label that on this review. I wanted to say something about what the coefficient of secant and cosecant do to those two graphs, but you can't really call it amplitude. Amplitude's not the right word. That's not height. I couldn't think of anything to call it. It's where your U's turn around, and I refuse to write that on a piece of paper. I'll say it out loud and record it and post it on YouTube for posterity, but I'm not going to type where your U's turn around in your notes.
Why point to the vertex?
The vertex of the two pieces. That works. To fit it on here, I'd have to go turnaround points of, I'd still have to say of the two U's, of the two parts. Well, they're not parabolas. See, I sometimes say they look like parabolas just to give you a quick mental image, but I don't want you thinking they are parabolas. So I don't know, y'all can think of something to label that on your review page, but I do want to make sure you understand that's what the 1/2 is doing. Vertex of each, I'm just going to say part again, because I refuse to write U's. It's going to be at positive 1/2 and at negative 1/2. I like that's negative 1/2. And actually, that wouldn't be smack on the y-axis. Halfway between these two would actually be right here. But I'm not going to be that picky on the test. We're trying to get a mental image so that, thank the Lord, when I'm handed a graphing calculator, I know enough about the graph of secant to go, hey, that can't be a circle. Or it's not, that's not a star. All right. I know this takes practice. I believe this is the best thing for you to practice with. The 2 additional, actually 3 additional videos that I posted in YouTube yesterday. If y'all read my email, you know, when I forgot to click record yesterday, I realized I had no video record of how to graph cotangent and cosecant. So I pulled those videos from my last year's videos when I was using pretty much the same notes. But those 3 videos that are on YouTube now on your channel that you go to, if you click the link in Momentum, those have additional examples. If you think additional examples would help you, then you can watch more video. I think Dominic or somebody said something about watching this on YouTube. Every teacher does this a little bit differently. I do it the way that I think is most understandable to you. But if you watch another teacher and they're doing it in a different way, it's likely to mess you up more than it is to help you. And that's why I encourage students to go to my videos rather than some other videos you find on YouTube. All right. Yes, ma'am. Sure. That's okay. May I see it? Well, no, actually, I think I have this. I may not. Let me just borrow your paper for a minute and I'll lay it on the screen so everybody can see what we're talking about. Is that okay if I lay it on the screen? Okay. Ooh, good question. Go ahead and finish your question. You're absolutely right. That -3 is a vertical shift of 3. So what were you going to ask, Hallie? And you're right. You're right. There's no x-intercepts for the graph of secant and cosecant unless they've been shifted. But if the vertex has been shifted down below the x-axis and it's concave up, it is going to have x-intercepts. That was a great question. All right, so if you did not give me day 2 today, that's fine. Get printed front and back, no problem. Just give me day 2 and day 3. The only reason I'm putting it off till Tuesday is I don't want to get a bunch of emails with pictures I'm trying to read or have to print them myself. So y'all just turn them into me Tuesday. Don't wait till Monday night to do them though. You'll be so lost by Monday night, you'll forget everything I've ever said about graphing trigonometric functions if you wait till Monday night to do it. All right. Yes.
The homework for that.
Okay.
Number 6.
All right. Do you mind if I lay your paper on the screen and you ask your question? Would that be okay?
Yeah.
Okay. Number 6.
When you look at 2 points, do you just divide by 1/4 pi?
Yeah, and this happened in one problem of day 1 homework. The coefficient of x happened to have a pi in it. And when you divided all 3 sides by pi, you didn't even have to count by pi's on your x-axis. You ended up just counting by 1s. So yeah, on number 6, when you divide all 3 sides of this inequality by 1/4 pi, you're just going to end up counting by something that doesn't have pi's in it. Is that all you needed?
I believe so.
Okay. Yeah, that happens sometimes. All right. Now, what this spending an extra day on graphing has done to us, just so you know, I thought it was necessary and I'm fine that we did it, but today we were supposed to get halfway through 4-7. Obviously, we're not going to, so that's going to eat into our review day. But like I said yesterday, I feel better without that review day now that you're only studying for part 2, rather than when you had 8 whole sections I thought we were going to have to cover on that review day. You don't really need it review day. If you can email me at home anytime, that's fine. So I brought 4.7 with me. I told y'all to go ahead and bring all your notes with you in case we ended up stopping in oddball places. Maybe we can get through at least objective 1. And talking about inverse trig functions. And honestly, this section for most people is a little bit difficult, just like division was a little bit difficult after you'd spent a whole year multiplying. It's hard to learn to think backwards. And that's what we have to do with inverse functions. Instead of me asking you, what is the sine of pi over 4? I'm going to be asking you, what is the angle whose sine is square root of 2 over 2? And you're going to have to tell me that angle is pi over 4, but actually there are 2 angles whose sine is square root of 2 over 2. Where else would you have an angle whose sine is square root of 2 over 2? Not only the first quadrant, but where else? Third quadrant, sine would be negative square root of 2 over 2. Where else would you have an angle whose sine was positive square root of 2 over 2? Second quadrant, first quadrant and second quadrant, your y's are positive. So you'd end up with a first quadrant angle and a second quadrant angle if I ask you for inverse sine of square root of 2 over 2. All right, that gives you an idea of where we're headed. But to figure out what we know about inverse sine, let's first graph the one real quick period of sine x. Don't worry about this negative part, just graph sine x from 0 to 2 pi. It should take you less than 5 seconds. Go. You know that sine is 0 at its endpoints and its midpoint. And if we use the interval from 0 to 2 pi, it has its upward hump before its downward hump. That's good enough. Now, what was the deal with inverse functions? Before I could say a function definitely has an inverse, what did I have to check? A function only has an inverse if that was a long time ago. A function, let me back that up. A relation is only a function if it passes the vertical line test, right? That means for each x, there's only one y. What was similar to that to see if something had an inverse? It had to be 1-to-1, which means it had to pass the horizontal line test. If you put a horizontal line anywhere on the graph and it touches the graph in more than one place, that's not a 1-to-1 function. And if it's not a 1-to-1 function, it doesn't have its inverse. Have an inverse. Now, if we graph sine all the way from negative infinity to infinity, is it going to be 1-to-1? No, it's that roller coaster thing that would have infinitely many intersections with a horizontal line. So certainly over its entire domain, sine is not 1-to-1. What about just over this interval from 0 to 2 pi? Is it? It's not even 1-to-1 over one period. I could put a vertical line here that would touch the graph in two places. I could put a vertical line here that touched the graph in two places. So and just like x squared was not 1-to-1, and if we wanted to talk about the inverse of the squaring function, we had to just choose 1/2 of the parabola. We had to restrict the domain to either the left half of the parabola or the right half of the parabola, so it would be 1-to-1. Similarly, we need to pick a 1-to-1 part of this graph. We could use, let's see, if we just use from pi over 2 to 3/2 pi, that would be 1-to-1, wouldn't it? Yeah. One day, many, many years ago, all the mathematicians in the world sat down together, thumb wrestled, and the guy who won chose negative pi over 2 to pi over 2 as the 1-to-1 piece of sine that we were going to use. And he had the strongest thumb of the millennium. Calculators are now programmed so that if you use the inverse sine function, it will always give you back an angle between negative pi over 2 and positive pi over 2. That's what our calculator is programmed to do. So sine is 1-to-1 on the interval from negative pi over 2 to positive pi over 2. Again, a lot of other intervals could have been chosen, but this was the one selected by the powers that be. And on that interval, if we just listed the 3 ordered pairs that we've plotted, that's negative pi over 2, -1 for the left endpoint, 0, 0 for the middle endpoint, and pi over 2, 1 for the right endpoint. What's the range of sine over that interval? The lowest y value on that interval is -1. The highest y value on that interval is +1. So those are some of the things that we know about sine, the graph of sine, and we've just highlighted one interval over which sine is 1 to 1. Now, what do you know about inverse functions? We've actually talked about, in the section where we did some word problems, we talked about the sine, the inverse sine button on your calculator. We said it looks like the reciprocal of sine. The reciprocal of sine is what? Cosecant, and that's not the same as inverse sine. So you can't think of that -1 as an exponent. It's just like the difference between this and this are not the same thing. Sorry, those two things are not the same. This is not cosecant, it's inverse sine. And when you see inverse sine, you need to think y is the angle. Y is always an angle. You're looking for the angle whose sine is the given value, whatever the given value is. If I say inverse sine of square root of 2 over 2, you're going to give me an angle whose sine is square root of 2 over 2. Now, tell me something else you remember about inverse functions. What's true about the ordered pairs for inverse functions? Yeah, you just switch the x and y. So instead of -pi over 2, -1, inverse sine is going to have -1, -pi over 2. You switch 0, 0, and it's still 0, 0. You reverse pi over 2, 1, and it's 1 pi over 2. And so when I try to graph that, I'm going to need the -2 pi over 2 and positive pi over 2. Those are y values. I need to count by pi over 2's on my y-axis from -pi over 2 to positive pi over 2. And on my x-axis, I'll count from -1 to +1. And then I'm going to plot these 3 points, -1, -pi over 2, 0, 0, 1 pi over 2. Now, the way I've spaced my tick marks, you almost could connect those with a straight line. But you know the graph of inverse sine can't be a straight line. What do you know about the graph of a function and its inverse? How are they related? I graph x cubed and then cube root of x. How do they compare? Here's x cubed. The identity line. Yes, yes. This is x cubed. This is cube root of x. They're rotated 90 degrees to the right, which is the same as Emma was saying, it's reflected with respect to the y-axis. Now, you know me well enough by now to know that is darn hard for me to flip across the line y equals x. It's just almost impossible. My brain doesn't work that way. I have 3 points here. It's the concavity that's difficult for me. They look a darn lot alike. But this one, if I kept going, don't even write this on your paper. It's gonna, I don't even want to write it on mine. If I just kept going like this, the only thing that allows me to graph this is that kind of looks like cube root of x. This kind of looks like x cubed. That's the only way I can get it straight in my head. All right, let's do the domain and range real quickly and we'll quit here. So what do you know about the domain of a function and how that relates to its inverse? If all the ordered pairs are reversed, what was the domain in the original function becomes the range in the inverse function. And what was the range in the original function becomes the domain in the inverse function. So the domain of inverse sine is the range of sine. And the range of inverse sine is what we chose for that restricted domain, negative pi over 2 to positive pi over 2. You can only take the inverse sine of numbers between -1 and 1. If I say, what is inverse sine of 2? You should say, there is no angle whose sine is 2. There's no angle whose sine is bigger than 1. You can only take inverse sine of numbers between -1 and 1. When you do, inverse sine will always give you an angle between negative pi over 2 and positive pi over 2. What two quadrants is that? Negative pi over 2 to positive pi over 2. That's first and fourth quadrants. Quadrant 1 and quadrant 4. All right. We have 3 more minutes and I'm gonna use at least 2 of them because I think we need to see at least one example to help all that sink in before we leave. And we'll probably have to review it when we come back. Monday's a long time from now. But when I ask you to find inverse sine of 0, you have to be thinking, I'm looking for an angle. That's the first thing you have to think. I'm looking for an angle. And for inverse sine, it has to be between negative pi over 2 and positive pi over 2. I'm looking for the angle whose sine is 0. Sine is which coordinate? It's the y coordinate. So where between here and here is the y coordinate 0? Or, you know, it's got to be a number between -0.5 and +0.5 pi. So you got to call it 0, even though 2 pi's coterminal with that. All right, inverse sine of square root of 3 over 2. I have to give an angle between negative pi over 2 and pi over 2, because that's what inverse sine always gives me. I need the angle whose sine or y coordinate is square root of 3 over 2. If that's positive square root of 3 over 2, is it going to be fourth quadrant or first quadrant? First quadrant. And sine close to square root of 3 over 2, is that near the x-axis or near the y-axis?
Y.
That's where your y is almost 1. That is this 60-degree angle right there, only we're talking radians instead of degrees. So what would you call that 60-degree angle? Pi over 3. And last one, sine, inverse sine of negative square root of 3 over 2 would be that same 60-degree angle, but in the fourth quadrant. So what's its name? Well, I'm thinking This is 9/6, so that's 10/6, better known as 5/3. But 5/3 is not between -1/2 and +1/2. So what's another name for that? It has to be between -π/2 and +π/2. It's going to be -π/3. All right, don't do any 4-7 homework, but finish up your 4-6 homework, day 2, day 3, give it to me. Dominic, you can give it to me Monday, and these guys are going to give it to me Tuesday. Y'all have a great weekend.
I have a quick question.